week of Oktoberfest. This is Thursday. It means we are in data and AI stream this day. And it is my great pleasure to introduce you to the very first speaker on this day. You might remember Jens from presenting at the Oktoberfest a couple of years ago. And at that time, we focused at Snap, the visual programming language or environment or system. I will let Jens maybe explain exactly what Snap is in few words in just a minute. But at that time, we focused at Snap as the environment. And today I asked Jens to give it a spin and to show how you can use Snap to understand artificial intelligence on neural networks a little bit better. So without further delay, let me hand this over to Jens, and stage is yours.
Thank you, Vitaly, and good morning, everybody. Thank you for dialing in, for joining in. My name is Jens Mönig. I work at SAP at University Alliances, where we try to really raise passion and awareness for computing and for what you could do with computing. Today I'd like to share our thoughts about teaching the technology behind AI, teaching about neural networks. And for this, let me just share my screen to, okay, so I'm sharing my screen. When the current batch of generative AI apps with ChatGPT, it felt to us who are in education like a storm hitting us, like nothing would be the same anymore. Some schools changed the title from informatics to AI. It's used to be like an hour of code. Now it's an hour of AI. It's a storm that rattles everything, that rattles our foundation. When we try to teach about mathematical backgrounds of this and to actually program this, this picture of this storm, of a gale force storm, really stuck. And we've come up with this word GALE, and it's really an acronym for what our pedagogical thoughts are about. That this artificial intelligence that's now taken off is really something that is general purpose, that is pervasive through everything. It's not just about one kind of media, not just about text. It's also about music, about movies, about art. But there are also things connected to it that are slightly different from what we usually teach when we teach computer science. It's much more about abstraction, and a lot of it is about linear algebra, and there's this thing about evolution. And so I'd like to show you all of this in this language that we're working on here at SAP, together with researchers at University of Berkeley, that is Snap. Let me quickly show you Snap. Snap is a programming environment that runs in the browser hosted at UC Berkeley, and where learners can share projects. Here you see my projects. I can go to my projects page and I can browse through the projects that I made. I can play them right in the browser, like here's a fun project I made the other week that lets me walk through a maze, kind of like a Wolfenstein thing. And if I want to know how this is made, I can also look at the code right in the browser, and here's the code. I can run it. I can check it out. And this is our programming environment for a course that's called The Beauty and Joy of Computing at UC Berkeley. And in this editor that runs in this IDE, I can make new things. It's a blocks language, so we have blocks that do something. Like here's a block that moves this sprite to a random position. I can click on everything and it becomes live right away. And we've got a bunch of things in there that make it powerful to learn different kinds of mathematics. Like for example, when we have, here's a reporter block, that's a function block. that lets us add two numbers. We also have functional programming in here. So when we have a list, for example, a list, let's say 3, 6, and 9, we can map over this list in a very functional way and put this block in here. Now we have the 3 plus block mapped over a function. But in Snap, we also want to be more expressive with regards of linear algebra. And this is why we've also added a way to do programming, vector and matrix. So I can also just say 3 plus this list. And now I'm getting a new list where 3 is added to every item of this list. Or I can make another list, let's say 10, 30, which I add together. The first item of the first list is added to the first item of the second one, and so forth. So we get another list of 3 items where each corresponding items are added. And we can do the same thing for matrices. Like here's a way how we can do a matrix, like I can say the number 1, reshape it to a matrix of 4 rows and 3 columns. And if I add that to this list of 3 numbers, I'm getting a column-wise addition to this. This is a quite powerful way to let us do fun things with very few blocks. In fact, let me show you one of the fun things. So one of the things that we're teaching with Snap is that you can build your own block. You can think about an algorithm and program that algorithm. For example, I want to make a new function, a new block, and the block should be an operation. It should be a function that returns a value and that transitions from one state to another in a bunch of steps. So I can make a new block. Now I've got this new block and I can specify that start is going to be an input, an end is going to be an input, and the number of steps is going to be an input. So now when I apply this, you can see that I've already got this block, and I want to do something like I want to transition from 4 to 7 in 3 steps. So I want to get a list of numbers. Now if I click this, nothing happens because I haven't defined it yet. Now I can think about a very traditional way to program this would be to write an algorithm. I could first start by saying, okay, I want the difference between the end and the start, and I want to divide that by the number of steps. Then I've got 1 step. Now I actually want to make a list so I can get the numbers of 1 to n, and maybe I also want to keep the very first step, so I start with 0 to n, and I can map over this list. And now I want to get the sum of start to, whatever the number of steps is for each of these numbers. So this would be a simple algorithm. Let's try this out. I'm applying this, and I can transition from the number 4 to the number 7 in 3 steps. Note that I'm getting a list of 4 because the steps are the ones that are in between. So this is how you traditionally program an algorithm. Now, one of the cool things is that when we're using blocks, when we're using this kind of array-based programming, something that we call hyperblocks, that we can also use this on data in any dimension. So, for example, let's look, here is the Unicode of the letter A. Here's the Unicode of the capital letter A. What if I get the Unicode of Snap or programming? I get it. Well, what if I transition from this list of numbers to another list of numbers, let us say the Unicode of a language we at SAP use at ABAP. How do you transition from Snap to ABAP in 5 steps? So if I use this now, it's a list of numbers and another list of numbers. I'm getting a table of numbers, a list of lists. And I can round these, and again turn them into characters. And now I'm getting a list. I can transition from snap over OLAP to LIAP to AgeGap, EDAP to ABAP. So it works with any dimension. And that is something powerful. So we can even and here is a sketch. Let me sketch something. Let me, for example, sketch. So I'm getting a number, a list of points. And I can make a variable. I'm making a variable. It's called B. And I'm assigning B to a sketch. One thing that I'm going to draw. And actually, let me just draw this clef again. So now my variable B is the clef. Let me make another variable, A, and let me assign A to another sketch. So A is going to be, let me write snap. So now I have two sketches. What if I transition from A to B in 150 steps? If I click this, I'm getting a very funky table, which is essentially a list of tables, a list of tensor. This really is a trend, so I should be able to play it back. So for each item in this transition, I could draw that sketch. And now, watch what happens when I evaluate this. I'm morphing one sketch into another one. And this uses the exact same algorithm that I'm using to trigger. Let me actually do this again, backwards. I can transition words. Isn't that great? That is the power of linear algebra, that with just a few functions, with just a few operations, we can do very complex things because the underlying idea doesn't change. And this is how we traditionally program. Now, when we're talking about AI and neural networks, this GALE acronym really is features some of the things that we try to focus on. Like when talking about AI, about neural networks, it is really about abstraction. And we're comparing patterns. We're not comparing for equality, but we're trying to find things that are similar, that belong to the same group. So this is traditional computer science. It's more kind to think about things, also about massaging data so it gets normalized, so we can compare it to other data that is not equal but that might share the same traits. And of course, when you're trying to abstract things, when you're trying to group things together that are not equal, you're bound to make errors. So is something that is inherent when thinking about the mathematics of AI. It is also about linear algebra because we're working with masses of data in different dimensions. We're not just working with numbers, we're working with we're working with lists of numbers, with tables of numbers. So it's great if we kind of have a language and have a way to think about this where dimensions and dimensionality is irrelevant. And there's one really algorithm that it's all about, and this is what I'm calling the sales slip algorithm. I'm going to show this to you in a minute. And one more thing when talking about neural networks is that it's about evolution. Evolution is a gradual thing where something emerges out of running the same algorithm over and over again, changing little things. Something emerges that is bigger than the sum of things, and it mutates the way how the system works. So essentially, I'd like to start with a little bit of history. Back in 1881, there's this British guy who's really cool, kind of self-taught programmer, Oliver Heaviside, who invented really two of the main things of all modern AI. One is he invented a stepping function. A stepping function is essentially, if the number is less than 0, it's 0, otherwise it's always 1. It's a stepping function, and he used it for telegraphs. And the other thing that Oliver Heaviside invented is the notation for the scalar product of two vectors. So he worked with quaternions and with vectors, and he came up with this notation that if you take the scalar product of two vectors, you use dot. Really thought a lot about this, what I call the sales slip algorithm. Consider the sales slip. I'm buying a bunch of things in a shop. What is the bottom line? What is it what I have to pay? I've got a column with the quantities of things that I'm buying, and I've got the price per quantity. So what I'm doing is I'm multiplying every row, and then I'm getting a sum of all the products. That is the sales slip algorithm, and I'm going to show you in a minute how this is exactly how neural networks work. Now, almost a century later, after the Second World War, here's this guy, Frank Rosenblatt, at Cornell University, who, just as computers started, built a different kind of computer. Not a general purpose computer, but a computer that was modeled like how he thought. The works. Frank was not a computer scientist, and he thought that the way how the brain works could be turned into a machine. And the machine that he worked on was called a perceptron. And this is actually Frank Rosenblatt's machine, the Mark I perceptron. And the way it worked, the way Frank thought it worked, was there'd be different things that are almost like the human eye. Here's a retina, there's some projection of the things of the signals that hit the retina, and then there is the human brain, which is just a bunch of random associations that generate a response and that sort of adapt to what they see to recognize something. And it came up with this formula, how a perceptron might work to actually recognize something. So here we see some of the pictures of blood. So here's this Cornell University, and you can see how this camera, sort of with a bunch of lights, takes a picture of that. And here we see the projection of that onto a matrix. So this is sort of a digitization of the sea. And this matrix would then go into the connections. And you can see that, the neural network quite literally was a maze, a network of wires that connect the sensors with each other to find relations. And this is precisely what I'm going to try to show you how this works in Snap, how we're teaching it. So all this research is sponsored by the military. So please bear with me now that I show you some military data. Here's a data set that is often used for machine learning. That is sonar data. Sonar data this is a bunch of pings, sonar pings. And it's the signal echo that comes back when pinging something. And it has 60 features, kind of 60 signals for each ping. And then the last column is what it is. And if it's a 0, it's just a rock or a piece of wood. But if it's a 1, it's a metal cylinder. It's a sea mine. And so the research was, how can we recognize a sea mine from a sonar ping? Let's actually, look at this data. So I'm going to set the data to the sonar data. Now I've got the data, and I can look at the first item of this sonar ping. And I see the first item is just a row of signals, and the last one tells me this is not. We can visualize this. Let's plot this data. Actually, it's just a lot of numbers in between 0 and 1, so we're not going to see anything when we plot this, right? Just very little bit. But we can easily scale it. Remember, Hyperblocks. So we just multiply this whole list by 200. Then we should be able to see something. So now we're seeing a bunch of bars. Let me actually just center this so it looks more like a sound signal. So this is what just a piece of rock would look like. Now let's look at the last item. The last item, you can see here is a bar. This is what a mind looks like. Let's just eyeball some more. This is again just a rock. This is a rock. This is a mine. This is another rock, another mine. I'm finding it difficult, and I've gone through this hundreds of times. I cannot make out any pattern, whether something is a mine or not, from these graphs, from these pings. So the idea was, let's try to use Frank Rosenblatt's perceptron to find a pattern. And to find a pattern, let's actually make another object. I'm going to call this perceptron. And this perceptron should answer something. I want to ask this perceptron to predict the outcome. So I'm asking the perceptron to predict the data when I'm taking the first one of this data. I want it to predict an outcome, whether it's a mine or not. And, let's actually try this. Now, if I click this, nothing works because I haven't done anything yet. So for the perceptron to work, the idea is that it has a bunch of weights. So I'm making a variable weights only for this object. And the weights are just random numbers that are initialized, with random numbers in between -1 and +1. So we have a block for that in Snap. If I click this, I'm getting a random number. Now it's either 1, 0 or -1, and a decimal point in here. Now I'm getting all the numbers in between. I'm getting a random number in that whole range, a decimal number. So I've already shown you the reshape block. Like when I have the number 1 and I reshape it to 4 by 3, I'm getting a matrix. If I'm just reshaping it by 1 dimension, I'm getting a list of numbers. Hey, and if I'm putting a list of numbers into this through Hyperblocks, now I'm getting a list of random numbers. Okay, with this, I can now initialize my perceptron. I'm making a new function that sets up my perceptron for the shape of the data that I'm trying to use on it. And what this does, it initializes the weights to this random list of the size of the shape. Now, when Frank Rosenblatt worked with perceptrons, he noticed that it's better to always have one additional value in it. And this is what he called the bias. So we're reshaping it to the shape plus one additional weight. And the bias is something we always need to remember. So now, when I look at the sonar data, I can initialize my perceptron with 60 features, because we get 60 signals. So when I click this, I'm expecting a list of 61 numbers here. And I'm getting a list of 61 numbers. Okay, so now let me actually request something. So now the perceptron needs to answer something when I'm asking it to predict something. So I'm making another function for predict, and it should predict something when I pass it a sample data set. And what it predicts should report. Remember when I showed you this? It's the exact sales slip algorithm. This is what Frank Rosenblatt said. So we're multiplying all the inputs with these weights. We're using the step function on this, and then we're getting an output. Let's actually try this. And since we're using Hyperblocks, we can do this exactly like we're taking the data sample, we're multiplying it with the weights. But remember, the weights is one more, so we actually need to also extend the sample with one, with the bias neuron. So now we've got the component-wise products. Now we're taking the sum of this. We've got the weighted sum, and now we need to take the step function. And the step function really is just that we say, you know, if this is less than 0, we return 0, otherwise we return 1. This is literally exactly what he did. Let's actually try this. So the first data, the first item is not a mine, so we should be getting 0. This is what we're expecting. Ha! But we're getting 1. Okay. So let's actually see how well we're doing with the whole data set. Let's write a little script that counts how well we're doing. So I want to count the errors. I'm going to initialize the errors with 0. And then I'm going to go through every sample in my data set. And actually, I'm going to shuffle it so it's not always the same thing. And now I know what the target is, like what I'm expecting, because the target here in my training data is always kind of the last item of the record. And I can say what I'm also getting, that is the output. And the output is exactly this, that I'm requesting predict from the perceptron with the sample. Now I can find out the delta, and the delta is exactly the difference between what I'm expecting and what I'm getting. So the delta can either be nothing, 0, or it can be -1, or so I need to change the errors when I'm counting them, not by the delta, but by the absolute value of the delta. And once I've gone through all the data sets, through all the data in the set, I want to see how well I'm doing. So I want to see the ratio of the errors to the size of the data set. And I'm really interested in success, so I'm going to invert this. Okay, let's try this with these random numbers. Let's see how well we're doing. We're getting 53%. Who would have thought? It's like we're taking random numbers, so we're basically having a 50-50 chance to whether something is a mine or not. Let's take a different set of random numbers and try this again. Another 50% chance. Let's try some more. 48%. So it's always around 50%. Now the idea was that since we already know from this data set whether it's a mine or a rock, we should be able to let this perceptron learn from it. So let's try to make it learn and make another method that says learn. And we're sending learn to the perceptron, and we're learning from the delta. And learning would be another method where we're getting an error and we learn from our mistakes. Learning for a neural network means we're adjusting the weights. We're changing the weights. And when we change the weights by the delta, that's surely not right because we're changing all the weights by the same amount. So what we need to do is we need to change them by how much they contribute to the error. And that contribution is depending on the input. Now the input is here. It's a script variable that is only scoped to here. So we also need to remember each input in the perceptron. So we're making another feature that is called inputs. And up when we're getting it, we're caching the inputs. And now we have them again down here. But again, since the delta has something, so we're changing the weights with the inputs. We also need to, again, do the bias neuron. And if we're doing this, we're just totally fitting the neural net to this, so we're to this single sample. But we want to find something that works for all samples, so we don't want to go all the way, but multiply it with a small number. And the small number can be a variable, and this is called the learning rate. And the learning rate usually is initialized with, let's actually initialize this here with, you know, like 0.5 or 0.1. Let's initialize it with 0.1 and hide it. So it's as simple as this. We change the weights for the delta. Let's try this. So I clicked on this once, I got 48%. Let me click on this again and see it changed to 59%. Let me click on this once more, and it's at 66%. And when they noticed this, they were elated. From a 50-50 chance, now we're at a 2/3 chance. And every time we click on this, this is called an epoch. We're going through every value in here. So if we click on this again, it keeps learning. Now we're up at 70%, and we can visualize how this works. Let's try this. So this clunky function can be exchanged for something more nice. Instead of having this function that steps, they thought, let's use the logistics function that really distributes all numbers evenly and nicely on an S-curve between 0 and 1. So now we've got this function, and we can maybe see how it works. So let's make a log. Let's actually initialize the log to a list. Once we're done, let's add the errors to the log. And let us plot the bars. Something like this, and do this forever, for a while. So let's start again with another set of random inputs, of random weights, and see how this learns. And we can see it learns very quickly, and we're 76%, and this is pretty great, but now it seems to stall and not get better. And, you know, while around 78 to 80% is really great for financial investments maybe, it's really not so great when it's a life and death decision. And so the question for a long time would be, how can we make this better? And one idea was to actually research into how perceptrons work. So the next thing that happened was that in 1969, Marvin Minsky and Seymour Papert researched into this at MIT, and they wrote a book about perceptrons. And instead of using a big data set, they started with a very simple data set and started to think about, you know, what happens at the end of the day? We reflect, has it been a good day? And among psychologists, there's sort of consensus that, you know, it's a good day if I did something meaningful, if I've done something with others, and if I've done something for myself. So this is a very simple thing. We can look at this data set. Here's a data set, you know, has it been a good day? So yeah, if I've, you know, done something meaningful, done something with others and had time for myself, it's a good day. But you know, what if I've done something meaningful, done something with others, but didn't have time myself? I'd say it's still a good day. The next day might be the same thing. So here's a rule that, you know, if two of these happen to be the case, then it's still a good day. So let's try to make our perceptron learn that. Instead of the sonar data, let's take all of the first of the days. So that cancels out the columns. And let's set up the perceptron for 3 features. And let's maybe increase the learning rate so we're seeing something more quick. And let's actually try this. Let's take some more. So we're seeing it learns perfectly. It can learn whether it's a good day, no problem. So the next thing Minsky and Papper did was, let's try another data set. Let's try a data set whether something is a yummy pancake. And you can think about a yummy pancake as something, you know, a pancake, if it doesn't have anything on it, like it doesn't have mushrooms, it doesn't have Nutella, it's meh. But if it has mushrooms, that's yummy. If it has Nutella, it's also yummy. If it has both mushrooms and Nutella, it's maybe not so yummy. So this is an either or they said an XOR problem. And so here's the pancakes data set that reflects this. It's nice if it's got mushrooms. It's also nice if it's got Nutella. If it doesn't have anything, it's not so yummy. If it has both, it's also not so yummy. Let's try this even simpler data set. So it only has 2 features. And when they ran this through Rosenblatt's perceptron, they noticed it doesn't learn. It can't do this very simple thing. There's a reason behind this, because the data is not linearly separable. And they wrote a whole book about this. But the problem was, wait, if it can't even learn whether a pancake is yummy, it really isn't worth working with. So for a long time, people were sort of despairing, and Frank Rosenblatt was already kind of thinking that, you know, hey, maybe what one perceptron cannot do, maybe 2 perceptrons can do. So what if we have a bunch of layers? So what if we call, you know, one layer, one perceptron, we call it a hidden layer, and we call, you know, the final perceptron the output layer. If we have 2 layers, maybe we could do something like this. So let's try to do 2 layers. So we need to initialize 2 layers. First, the hidden layer, and then the output layer. But now a layer needs to have more than one output. So we need to specify the shape of inputs and outputs. So this would have 2 inputs, so let's say maybe 5 outputs. And the next layer, the output layer, should have 5 inputs and a single output, whether a pancake is yummy or not. So we need to change how we set up these layers. So shape now is a list. So the weights need to be a matrix, and the number of inputs would be the number of columns in that matrix, and the number of outputs would be the number of rows in that matrix. Notice that in Snap that I made this a clone. A clone means that now this object is inherent in every change that I make to its parent. So let me visualize the hidden outputs, the hidden weights. Now let's initialize this like this. Okay, this seems legitimate. I've got two sets of weights. So now I need to change this. When I request the output, I need to first route it through the hidden layer and then to the output layer. So what I'm getting is a pipe that takes my data sample and first sends it to the hidden layer and then sends what it gets back to another layer, which is the second layer, the output layer. Okay, since weights are now a matrix, I need to slightly adjust this. I can't just multiply it with this. I need to map over it. Now this should work. Now I'm getting an output, which is a list. Okay, my delta could also be a list. My arrows now need to be the sum of this list. And now I need to also change the way how it learns. And that's a problem because now I need to adjust the weights of the output to the delta and then also the weights of the hidden layer. And when they tried this, it didn't work. So we need to get this error, this delta, and need to distribute it over these layers. And distributing the error over a bunch of layers backwards, that is called backpropagation. That's the term Frank Rosenblatt came up with. And he tried to do it, but he failed and it didn't work. What's worse is that shortly after this book came out, Frank Rosenblatt tragically died in a boating accident. He drowned. And along came personal computing, and this kind of AI was suddenly no longer that interesting because everybody was working on other things. And it took 15 more years until a bunch of other researchers, among them Geoffrey Hinton, David Rumhard, found out how to do backpropagation, and they published it in 1986. Until that problem was solved, and even after they solved it, they didn't leave it for another 9 years themselves. So let me show you what they came up with real quick. So they said, okay, backpropagation really is another pipe. It's another pipe where it's actually a function that first gets the delta and then requests learn from the output layer. Then it gets back a new delta for the next layer. The new delta it gets back, it channels through the hidden layer. It needs to be another pipe. This also means that learn needs to report something. It needs to report something back. It needs to report back the next delta. Say the next delta. And the next delta, it takes the delta and it multiplies it with the inputs, and it multiplies it again with the inverted inputs. This formula is the Nobel Prize for Physics 2024. So we need to adjust this slightly because this is also a list. So we need to say, okay, we need to map over the delta. And then we need to take the sum of it. And same here, we need to map over here. map over the delta here. And now what they did is they found out that it's even better if they also take the weights into account. Then it's a little faster. So they map over the weights and take out the bias neuron. And multiply that with their little formula they came up with. And this is how they got back propagation to work. And now I'm really excited because often when I code it up myself, it doesn't work. Let me try whether it actually works. So let's start with a new set of random numbers, and let's actually run this. And wait, it's not working because we are not setting it. We need to set the next delta, of course, before we get it back. Try this again. So now the weights are changing, and we can see it is totally able now to solve the XR problem, to find out whether a pancake is yummy. So now that this problem was solved, we can also use it on, the sonar data again. Let's look at the sonar data. Let's do the same thing. Maybe reduce the learning rate a little bit. And let's initialize it for 60. And maybe have another hidden layer of 5. Let's do the same thing. And try how this works now. And we can see we need to scale this a little bit. Let's actually scale this a little bit more. We can see it's already learning the sonar data. It's already above 95%. And so this really is the magic of neural networks, that we can now, using hidden layers, we can do complicated things. Hidden layers is something that when we add more layers, we just add more to the pipe. The forward pass and the back propagation. This is called deep learning. If you look at the formula, this is all the code it does. This isn't really all that hard if you're at college level. So if you're not teaching this by now at college level, you probably should be. So this is kind of what we've been thinking about this GALE. Now, this was maybe very mathy and very kind of, difficult. And we've been thinking about how could we use this even in school and even make it such that we can have fun activities in school. And let me show you something that we did in Snap. So we put this into a library, and it's a neural networks library. We have libraries here. It's a neural networks library where we can just use neural networks as a resource. So, and it'd be fun to use maybe our own data. So let me just very quickly try to kind of actually record own data. So I got one sound. I'm going to call this harmonica. Let me record another sound with my recorder. So now I've got another sound that is called, I'm going to call recorder. Now a sound really is also nothing but a signal. So I can get the signals that are called the samples of the harmonica. This is what I recorded. At first I didn't play anything, but then I played something, so I got these numbers. It's a very long data set of 334,000. I want to cut this up into chunks of 100. So I'm just going to leave this blank and say 100. So now I'm getting a table of chunks of 100. And I want to tag this. I want to tag this in which I, append all of this. And my harmonica is going to get the label 1. Now I'm getting a data set where in the last column They've all got 1s. So I can do the same thing with the recorder, but tag it with 2. So I'm going to put these all together into one big thing, shuffle them, and just take a small sample. The items, let's maybe just take 500 of these. And I'm going to assign this to my data set. So now my data is a bunch of sound samples, either from my harmonica or from my flute. So I want to make an AI. So maybe an AI could just be something like a variable. And I'm setting this AI to be a new neural network. And the topology should be 100 and 2. And you know, I can find out something about this neural network. Like I could get the model of this neural network. So now the model is just a bunch of weights. And I can visualize this. I can render this. Let's actually render this. And this is what it looks like. I can reduce its scale slightly and color negative values red. So this is what it looks like. So now I'd like to actually train this neural network, and I can train this neural network on my data. So I'm training AI on this data, and what I'm getting back is an error. So I can make another log where I can see how it learns. And so I'm just forever adding the result of one epoch to that log. And I want to see what's going on, so I'm going to plot the bars of training this. Let's see how this works. So let me actually try to train this. Wait, I need to do this. It's I need to initialize the log to be a list. Now it should work. So I'm training this, and I can see something here. It's not really learning. And maybe the reason is because I'm once again just having a single layer network. Another layer under a hidden layer of 5 neurons, then outputs. So this is now how my neural network looks like. Let's see whether it learns. So I'm going to try this now. And scale this maybe slightly down. And we can see it is already starting to learn. And it's already starting to learn quite quickly. And that is fascinating, because this data really doesn't mean anything. It's just random chunks of signals that I've recorded. And that is kind of interesting, because now when we train this data, we should be able to do something with this. Like, what if I take like the microphone samples? Taking the microphone samples, and I'm taking the first 100 of the microphone samples from my live microphone, and I'm trying to actually classify these with this neural network that I'm training. And you know, since it's live data, I might want to make this a little short, so I'm doing this 500 times. And then I'm going to switch to a costume when it's decided what it should be. And I would do this until, or whenever, you know, my microphone is above a certain threshold. I want to do this forever, otherwise I don't want to show anything. So let's look how well we're doing. It seems to be converging. I'm halting this, and I can validate the network. Let's validate my network on my training data. It's at 97% for the training data. I think this should be fine. So let's try to actually see whether it learned something. So I'm going to switch on my microphone. It noticed my harmonica. And it noticed my recorder. So this is something how we can bring in our own data and have some fun with it. And this is sort of our own vision to teach about the math, but also use it as a creative resource. And as a bottom line, we think that computational thinking needs an upgrade with linear algebra. We need to teach linear algebra earlier in school. And we also need to teach that AI is something that stands next to an algorithm. It's an alternative way to program something. So computer science, both modalities, still important to actually program something, because programming is to understand. And if we don't program something, we no longer understand what we're doing. And it's easier to just use the neural networks library as a creative resource so we can do fun things like instrument detection. And we should maybe really find out what to teach in school and really teach these algorithms and not just sorting. And thank you.
Thank you, Jens. I don't need to run it through backpropagation to make the statement that you made, my Jay. So I've seen something meaningful. I communicated with you. And today in the morning, I had a walk for myself. So I believe that this is a great day. Thank you so much.
Now you can have your pancake.
Yeah, now
Thank
I
you
would
for
need
having me.
to test the pancake. Thank you so much for joining. We are almost at the top of the hour, and we will be continuing with the next Oktoberfest session just in 2 minutes. I just would like to remind that for those of you who participate as well in our Oktoberfest contest, there are validation questions available, and you will find one for the session that you just watched in the chat, or as well, it will be added to the session description on YouTube and in SAP community. With that, Jens, thank you once again. Beautiful presentation. I think that if we would give you 1 more hour, you would build another LLM just from all these blocks. But unfortunately, we were limited in time. So for you and everyone else, have a good day and enjoy the Oktoberfest.
Thank you so much. Bye-bye.
Take care for now. Okay.